Okay, let's start the lecture again. So we are discussing continuous functions actually. So we have function f from R to R, and x naught is a point of this real line R. Then f is continuous at x naught. Then f is continuous at x naught if for each epsilon positive there exists delta positive such that distance between x and x naught less than delta implies distance between, sorry, not distance here, we are on real line actually. So we apply the usual metric to have के पास, that's this mod of x minus x naught less than delta implies mod of fx minus f of x naught less than epsilon. So that's the definition of continuity. Or you can write mod of fx minus fx naught less than epsilon whenever mod of x minus x naught less than delta. So what we do now, suppose we have two matrix spaces, say x d1 and x d2, okay, y d2, sorry, and f is a function between x and y, and this x naught is again a point of x here. In that case it was a point of R. So then we say this function is continuous at x naught if for each epsilon positive is the same, okay, if for each epsilon positive there exists delta positive such that this thing, such that, not the mod, because can't apply mod here because it's an abstract metric space here, so we can't even take the difference of these 2 points x minus x, we can't write that because it's any abstract space, so we don't have the algebra on these set of points. So what's the general notion of continuity? That's this. So d of x x naught is less than delta implies d of fx and fx naught is less than epsilon. Okay. So now suppose this is real line C. अगर ये रियल लाइन होगी उस केस में आप यहाँ से तो मॉड कर सकते हैं अपने मॉड ऑफ x माइनस x नॉट, because on this side it's well defined, x and x naught they are real number, they are the real points, but on this side you can't apply the mod. और अगर सपोज यहाँ से आपके पास ये जो y स्पेस होगा ये रियल लाइन होगी और ये रियल लाइन नहीं, x रियल लाइन नहीं होगी बट y is your real line, okay, then you apply the mod here, not on this side, huh? Then you can see d of x x naught less than delta implies mod of fx minus fx naught less than epsilon. So let's define it now properly. So next page, so there's a definition of continuous mapping, okay. Let x d1 and y d2 be two metric spaces, and this point x naught is in x. We say that this f is continuous. F is continuous at at x naught if for each epsilon positive there exists delta positive such that d of x x naught less than delta implies d of fx naught less than epsilon. Or in terms of sphere we can write, actually this means x belongs to the sphere with center at x naught and radius delta, implies, this should imply the point fx, it should belong to the sphere with radius epsilon and center at fx naught. So I can write it as or equivalently. एक्चुअली जनरल टोपोलॉजिकल स्पेस में जब आपने कंटिन्यूस मैपिंग को डिफाइन किया वहाँ पर आपने बताया था इनवर्स इमेज ऑफ ओपन सेट्स ओपन। तो यहाँ पर सबसे पहले हम स्फीयर्स को लाएंगे इसमें, देन वी टॉक अबाउट ओपन सेट्स इन जनरल। ओके, सो दिस मीन्स फॉर
हमने ऊपर लिया ना
या हाँ यस
हमने ऊपर लिया ना मैट्रिक x manual id
okay, oh sorry it's yeah you are right sorry it should be d1 here yeah? तो आपका क्वेश्चन ये ना कि ऊपर हमने d1 लिया है
yes sir, d1 and d2
oh right d1, so on this side it should be d1 and on this side it is d2, right? Sorry, so equivalently we can write it as equivalently for each epsilon, for instead of for each epsilon positive I can write for each sphere. Okay, for each sphere as epsilon x naught there exists a sphere as sorry it's as epsilon fx naught, not this it's as epsilon fx naught, it's like this sphere. Okay, the sphere with center fx naught and radius epsilon, there exists a sphere as delta x naught such that x belongs to s delta x naught, ये वही है distance between x and x naught less than delta ना, implies as this fx it belongs to s epsilon fx naught, where this is understood that this sphere is with respect to the metric d1 and this one is with respect to the metric d2. Okay, so that's a definition of matrix space, definition of continuous mapping. Okay, so you can take now examples, also examples of continuous mappings that you can also discuss here. So actually our main task is to discuss C01 actually. Okay, discuss our space, that's the space of continuous functions. So let's see that the set of all continuous functions or set of all bounded functions also we can take given a matrix space x, we define a bounded function also, a real valued bounded function. So this is the space of bounded and bounded functions and space of continuous functions. So these are two classical spaces that we'll discuss here. Space of two continuous functions, space of continuous function. Okay, so what's a bounded function? What's bounded function? So there any notation for bounded function or not? This is no. Let's denote the set of all bounded. Okay, so let x be a metric space. Let x be a metric space. Let x be a metric space. Okay. We say a function f from x to r where r is a real line is bounded. We say this function is bounded, okay, if there exists some key positive such that distance between fx and fy is less or equal to k, okay. This is for each x and y in capital X. So that's the definition of bounded function here. So this is a metric on x, okay. It's a function from metric space x to r. And likewise, we can define continuous mapping. That's already discussed actually. Continuous mapping between metric space and real line. Okay. So the set of all bounded function is denoted by bx, okay. The set of all bounded functions on x, set of all bounded real valued, you write this actually, bounded real valued, they are real valued also, bounded real valued functions on x is denoted by this space bx r, okay, or simply bx, because r is understood, it's a real line, so it depends only on actually x, okay, or simply bx. This is set of all bounded functions, and this set has algebra because sum of bounded functions is again a bounded function, difference of bounded functions is again a bounded function. So you can easily verify this. Home assignment, show that point-wise sum, okay, it's point-wise sum and difference of two functions in bx is again in bx, is again or again in bx, okay, or again in bx. So it's this bx is closed with respect to sum and difference actually. Yes. So sum means if you take two functions, you define f plus g like this, f plus g of x, it's fx plus, and this is well defined because fx is real number, gx is real number, it's a function from x to r. अगर यहाँ से कोई और space होता ना, abstract space y, then you can't define the sum like this, okay. Because you know that this fx is real, gx is real, so we can add these two things, fx plus gx, and sum of two functions is defined like this now. So this is well defined, and difference is then likewise actually this is fx minus gx, okay. Now you need to verify this sum and difference, they are both bounded functions. Now we try to define the metric on bx, okay, bx parametric define करेंगे, and then we will show that this bx is actually a complete metric space. So that's very important. पहले हम इस पर एक metric define करेंगे, and we will prove that with respect to that metric bx is complete. So exercise, let define a function, d on bx by d of f and g, because d is a function on bx, so it's a function from bx cross bx to r, okay. This is equal to the supremum of mod of fx minus, and this supremum exists because f is bounded, g is bounded, difference is bounded, so x runs over x, so which is always a finite thing, okay. This for each x it's a finite thing, this number. So you need to show that this D, this defines a show that D is a metric. Show that this D is a metric. Okay, is a metric on Px. तो इसको हम नेक्स्ट लेक्चर में डिस्कस करें इसकी कंप्लीटनेस एंड देन विल सी दैट जो कंप्लीशन थ्योरम एक्चुअली हमें करनी है ना एवरी मैट्रिक्स स्पेस एज अ कंप्लीशन वो हम इसी के थ्रू करेंगे. There are two ways to prove that theorem. One is on Muncri's, but that's a little abstract. So better way is this because they are actually classical spaces. So it is better to do the theorem with the help of these spaces Bx and Cx actually. So thank you. Now if you have any question you can ask it.